Hey everybody, it's Mrs. Peachy from WCA Physics, and I am going to be walking you through a practice problem in projectiles launched at an angle. For those of you that were in class this week, we started working through the problem in class, but then we ran out of time, so I wanted to make sure we had an opportunity to go through this one before your test next week. And it also is kind of a complicated problem, so I want to make sure we have a chance to walk through it. So I'm going to draw you, well, first I'm going to read off the problem for you. We're looking at problem 2 on page 101 of practice set E. Reads a golfer hits a golf ball at an angle of 25 degrees to the ground. If the golf ball covers a horizontal distance of 301.5 meters, what is the ball's maximum height? And then it gives you a hint. At the top of its flight, the ball's vertical velocity component will be 0. Alright, so I worked through this a number of different ways, and I'm going to draw your attention now to my notebook and kind of flip the screen around so we can all see what I'm doing here. So let's look at kind of the layout of this problem first. And we're going to set this up X and Y axes. Okay. So total distance a ball travels is going to be 301.5 meters, which is here, right? And we can say that the ball has a parabolic path that it travels. We don't know how fast it's going, so we really don't know much about this path other than the entire length of it is 301.5 meters. So we want to find that the maximum height of this parabola. What we can say, we know that half of the length of the parabola is where the maximum height will be. If the total length of the distance traveled is 301.5 meters, then this is going to be 150.75 meters to that halfway mark. Okay, so we'll kind of start with that. The other thing we can see here is, we don't know this height, y, so we're going to figure that out later. But we can also divide this into its velocity vectors. We have no idea how fast this ball is when it leaves the tee, but we can use some of the information we have to determine that. Okay, so we can divide this into horizontal and vertical components of velocity as well as of displacement. Remember, they're all vectors, so they can all be divided up. So we can say, this is a 25-degree angle, remember? And we can say that it left the tee at some velocity v. Don't know what that is, but we do know that if I want the velocity vector on this side, my y velocity vector, I can do the sine of 25 is equal to v sub y over v. So we can say v sine 25 is equal to v sub y. We can also do the cosine of 25 is equal to v sub x over v. So that would mean that v cosine 25 equals v sub x. Okay? The other thing that it tells us is that at this point in the flight of the golf ball, its velocity, or its y component of its velocity, is 0. So it only has the x velocity. So we know right here that that point is going to be 0. So we'll kind of tuck that away for later. We also know that the x velocity does not change throughout its entire path. So whatever its x velocity is here will also be here and wherever else we can choose along the path that it will take. So now I'm going to be using the kinematic equations found on page 99 of your book. And these are dealing specifically with projectiles launched at an angle. Notice you only have one equation dealing with your x components because velocity is constant, so we have no acceleration. So All the other equations are just, not existent. So here, I'll set that up here. We have delta x equals, and vi cosine theta times delta t. Okay? So we're working out kind of linking the actual displacement with the velocity, right? So this is just basically a rearrangement of the distance over time equals velocity, so velocity times time equals distance, right? So we're just kind of rearranging that equation to get this one. Now, what we kind of talked about in class is that the only scalar quantity in this whole thing is time. So no matter how fast it's going at any point along its path, it takes a certain amount of time to reach this point. And that time isn't going to change if we're looking at the x components or the y components. You'll have the same time either way. So we're going to solve for t, for time, because time is kind of, it's the bridge that connects both sides. So t, or delta t, equals delta x over vi cosine theta. Okay? So that's one way to talk about time. Another way to talk about time is using one of my kinematics for my y variables. And if you look at the third equation listed on page 99, the equation actually is v final, v sub y final, equals v sub I sine theta plus a sub y, which is basically just gravity, right, times delta t. So remember, since we're looking at this point right here, we can say that v sub y final at that point is 0. So we're going to call that 0. So using this now, we're going to solve for delta t. So I can subtract v sub I sine theta from both sides, and I end up with a negative v sub I sine theta. And then I'm going to divide by my acceleration. And just so we're clear, when we finally do the math here, this is negative 9.8 meters per second squared, so negative divided by negative is a positive, right? So that altogether will kind of cancel each other out. Okay, now taking this equation for time and this equation for time, remember the times are the same either way, so I'm going to set these guys equal to each other and substitute in some numbers. Okay, so negative v sub I sine theta all over a y equals, and I had delta x over v sub I cosine theta. People sometimes get frustrated when I don't substitute numbers in right away, but just remember that variables mathematically do the same thing as numbers, so you just need to be comfortable multiplying variables by each other. So now we're going to substitute in some numbers that we know. We don't know our initial velocity, so we're just going to leave that as v sub I. V sub I times the sine of 25 divided by negative 9.81 meters per second squared equals 150.75 meters divided by v sub I cosine 25. Okay? Now if you cross multiply here and do a bunch of rearranging, you'll end up eventually with v sub I squared equals, what is it? Well, we end up with 1,479 divided by cosine 25 sine 25. Then you do that math and take the square root of both sides, and our final answer is v sub I equals 62.1 meters per second. So that's not where we end this, because that is our initial velocity, right? That's all that we have so far is the initial velocity. I'm going to take that number, that 62.1 meters per second, I'm going to go back and substitute that into one of my initial formulas. Because initially I said, here, delta t equals delta x over v sub I cosine theta. So I want to know what delta t is. Delta t equals delta x, which we said was 150.75. And v sub I was 62.1 times cosine 25. And when I do that math on your calculator, you'll end up with a time that is equal to 2.68 seconds. Now we're getting somewhere. Now what I want to do is I'm going to go back to page 99. And I want to use this equation at the bottom to solve for delta y. And it's kind of a long one. So you're going to substitute the 2.68 seconds in for time here and here. Remember, acceleration is negative 9.81 meters per second. That makes a big difference in this problem, okay? Negative 9.8 meters per second. Because when you do that, this number ends up being negative, and this number ends up being positive. So you'll end up with a larger number minus a smaller number, and that will give you your delta y. Okay? So, I do not plan on finishing the work here for you. That was all of it up to a point. You guys can plug in the last of the numbers into your equations and come up with the final answer there. As usual, if you have any questions or concerns, feel free to give me a call at extension 2204, or you may send me a webmail message. Have a great day, everybody.